think we're back from the break. Mihir, are you ready to take over? Oh. Okay, Mihir and Annie, go ahead and take over the next session.
Okay. So Annie's going to take the first two plenary talks, questions regarding that.
And they are, remind me again, where do we start? We start with Angelos, or we start with Elena?
No, Gilly.
Gilly. We start with Gilly. There we go.
Okay, so okay,
there we go.
I have. There's a question about.
Yep, I have it. So Gilly has a question about pip comment in the chat, and he put it in Slido. Then Sherilyn looks forward to the outreach white paper, and she wonders if the sunback capability could be linked. And Gilly replied in Slido, then Emily Mason has the comment on the limitations on the radial filters for the AIA imagery. And shall we just what is the best way to do it? Would you like me to read out the discussion real quick, or shall we?
I can sort of summarize what we talked about there. One of those has like 20 comments.
Yeah, I think that would be the best, because So
interesting. It's distorted a little bit on the shared screen now. That first comment at the top. Oh, there we go. So I'll just go from top to bottom right there real quick. So we were talking about limitations of the radial filters and like finding things that aren't really there in the data. And I think that we kind of said, well, there's data all the way down to the noise floor, and most of these things, at least the methods that we were talking about specifically, aren't. They're kind of like isotropic. They're the same, at least radially. So it shouldn't, the relative brightness between things shouldn't be too wrong. But yeah, I'm working on that that kind of work right now. Pip command, yeah, if you want to have your desktop background be the images of the sun, like right now or 10 minutes ago or so, I put that into that answer there, but you just pip install sunback and then sunback.run is the command. I try to make it as easy as possible. So this next one, so at a particular part of the talk, I was showing how you can interpret the width of a spectral line entirely as if it came from thermal effects. And the question is sort of, why is that valid? And just for those slides, for that particular run of the model, all flow in the corona was deactivated. It's one of these toy models where you can really like tweak knobs however you want. So we just set all the velocities to 0 everywhere, which means that the only thing that's happening is that there's a bunch of thermal Gaussians of different widths and intensities being co-added. And so the cool thing is, if there weren't any extra width, then we could use the temperature measurement pretty well above those plateau heights at least. But it's really one of the main things about this kind of work. It's like, okay, you have one number that you have, and that number is how wide that spectral line is. And it's supposed to tell you about like Alfvén waves and temperature and the solar wind and all these things. And that's why the forward model is required. You have to actually know how to split it back out. Like say 50% of the width always seems to come from thermal. If that was true, which I just made up, if that was true, then you could always say, okay, we're going to take half the width and call it thermal. But I think it's going to be more complicated than that. That's the last one that's showing right now.
By the way, Amir pointed out that the whole conversation thread on Slido for Emily Mason is worth reading. It has like 19 replies, and it's about radial filters.
Yeah.
So then there are questions for Elena. So there is an anonymous question about how exactly do we set up the helicity parameter in the tethered Gibson and Low. Well, Elena replied that we are not explicitly setting it up, but that is not entirely true. It's one of the default parameters. So the default value is negative, and we will not be changing it for the DOICMAM challenge, which is the probabilistic study of the CMEs. However, for the CME challenge, we can change it. There is a way to switch the helicity in Gibson and Low. Then another question for Elena is what did we is whether we try to estimate the scattered component. Oh, that's sorry, that was the question for Gilly. The question for Elena from Christian was how much time does it take to run the 54,000 simulations? And Elena, would you like me to just read it out real quick, or would you like to summarize it yourself? Okay, I'll just read it real quick. Well, we did test it in batches of 20,000 runs, which so it does. So I will take that question because I'm also in that project. The actual CPU time is rather big. However, we are running it on supercomputers, so we can run many processes in parallel. So 2000 in parallel take about 7 hours running on 2000 cores. Well, there will be additional time for post-processing and so on. Then there is a question from Pradip about the rotation of B and whether it's related to the unwinding of the CME field, or are there indications of helicity injection? And again, Elena, would you like me to get this talk, or would you like me, do we have Elena at all here? Well, she is. Okay.
I can also take that scattering question real quick.
Okay.
Hopefully this is not a problem if I screen share briefly.
Go for it.
Yeah, so I was just asked, have we estimated the scattered component versus, I guess, collisional excitation? And so I just wanted to show in this 2020 paper last year, I guess. And these plots are the same. It's observation height above the photosphere. And in this case, we're looking at the resonant intensity, the resonantly scattered intensity over the total as a function of the wind speed. So when there's no wind, in a lot of these cases, you get a lot of resonant light. But then as you increase the amount of wind, you get Doppler dimming. And so there's really, in this middle and upper corona, a lot of variation in the intensity of the resonant component, for sure. So this was a result that I didn't really think of too much as a result because it doesn't mean that much to me, but other people were like, oh, hey, that's cool. I also have absolute intensities if y'all want to see those, but I can end this share now.
Oh, and thank you. I also wanted to mention to everyone, feel free to raise your hand if you have additional questions or comments related to any of those topics we're discussing. And I'm keeping an eye on the Zoom raised comments chat. Then there is a question about the helicity injection of the magnetic field. Elena, would you like to summarize it, or would you like me to summarize it?
I think Elena's back now, so she can answer.
Yes, I apologize for being away for some time. Yeah, so we don't set explicitly the helicity right now. We're using the default negative value in the model. That's for sort of for future studies to play with helicity. But Annie, if you have something more to say, please feel free to jump in.
Yeah, I already replied. We're not planning to change it for DOICMAM project, but there is actually a parameter there, and yeah, and it can be easily changed. And Sarah will talk about it later in her talk in the next session, in the session after the next. So yeah, it can be changed. But then there was the question about the rotation of the magnetic field, whether it's related to unwinding of the CME field, or are there indications of the continuous injection of helicity from the foot point motion? And you replied to it. Would you like me to read it or summarize it, or would you like to
I can just quickly summarize, and sorry for being confusing. When I said rotation, I meant the time evolution of different components of the magnetic field as you observe them at 1 AU when the CME passes by the spacecraft. And by rotation, I meant that, for example, the BZ component changes from being positive to negative, and the X component also changes the sign. So that's what I meant by rotation. But that implies that the magnetic configuration of the CME that passes by the spacecraft resembles the flux rope or flux rope-like structure. So we were trying to reproduce this time evolution of different magnetic field components with our simulation.
Thank you. I also wanted to ask the audience if you guys have any questions or comments regarding the two talks by Elena and Gilly, and feel free to raise your hands or feel free to do the Slido, and you can also add more questions to Slido at any time. Well, I see no raised hands at this moment, so there is always an option to ask questions in Slido. And for now, let's just go to the to the comments on the next talks. And Mihir, would you like to?
Sure. So the first question was, let me bring that up in the Slido here so you can see it, is for Angelos, and it seemed like a comment, but Joan asked that question about CME properties of thousands of projection effects, and a question about whether there are true properties. LASCO observed many CMEs far from the limb, therefore true properties are different. Average CME mass will be higher and lower. And Angelos, I don't know if you're still there because I don't see a reply there. And it may be, yeah.
It looks like Angelo is not currently in this session.
Okay, so any questions regarding Angelos, or we can defer it till later. The next, there was a question for you, Anna, about whether machine learning, let me bring that up so that you can see it, whether machine learning is a suitable approach to get observed properties of CMEs from the grid. That's for you, Anna.
Yeah, and as I replied in Slido, yes, it absolutely is a possible venue to explore. I was in a project where we looked at the synthetic IQ-UV as in comp data near Sun, and tried to use these to estimate, say, BZ, and we had some success with that. Of course, punch data will be very different from what we used, so it will take a different machine learning model. But yes, I'm absolutely looking forward to seeing what people can come up with.
So there was another, Angela has joined the room, so maybe, but let's finish this off, because I think that's an easy question for both Elena and Anna to wrap up. I think it's from Sherilyn. Yes, I'm the Punch Outreach Director, and I'm interested. There were 4 replies to that in getting the Gamera MHD simulations and try to use it for low vision learners. So there are a lot of probably computer outputs for low vision learners that we don't know about. So I will be open to meet and discuss. However, right now I would like to point out that there are non-computer models of CMEs and such. And here's one. I have this styrofoam ball model. I don't know if you can see it.
Wonderful.
So and then I made it for a completely different project unrelated to punch and CMEs. I made it for the Coronal Veil project. But I would like to point out that in magnetic field, the Lorentz force has 2 components: magnetic pressure, magnetic tension. and both are mathematically very similar to, say, pressure of an air balloon being blown, and pressure of and also tension of a rubber band, and both of those kind of just beg for tactile demonstrations, right? And this is just a thought.
So one of the reasons I brought this up is I thought it may be that there are others who could also contribute to this kind of other modelers that might also want to, modelers or data analysis folks who might also want to contribute to the same audience and work with Sherilyn on that. So if you have any ideas that you might think kind of be applicable here, and I see a hand here from Pradeep. Did you put it in the Slido? Okay, let's see.
That would be great, Mihir. This is Sherilyn. Thank you, Anna. And we are in email connection with Anna and Elena now in regards to a beautiful slider tool that she just sent to me.
Oh,
and so
yes.
we're looking forward to more conversation tomorrow. And thank you, Mihir. Totally, yeah, open to other ideas for tactile representation, for animations, for the planetarium films, for digital interactive lessons. There are many media in which these kinds of things can be brought to bear.
Right.
May I share my screen real quick? Just to show the web tool that Sherilyn mentioned. It's basically the link is in Slido, but it's basically one simulation and polarized brightness in a semi-interactive way that would allow you to kind of rotate the field of view around, and also, I mean, in different ways, and also change the time of the simulation. So that's it.
Such a thing could be adapted into an outreach tool unto itself, right? And I want to have more conversation tomorrow morning about that and other ideas. And your tactile, your balls there are really excellent too with blind and low vision learners. I mean, we can create them in the way that they can touch these things and feel and experience as well. So yeah, high tech and low tech all work beautifully.
Okay, so how do I get someone to ask a question who's raised a hand on here?
So actually, I think Kelvin has already given Pradeep the ability to unmute. It looks like he's unmuted. So I think he can.
All right, perfect. Go ahead.
So
go ahead.
Yeah, thanks. I just have a follow-up on this camera type simulations. Now, if I understood correctly, please correct me if I'm wrong, that these simulations use a particular type of flux rope and they propagate using the MHD equations and try to construct the polarized brightness signatures. But is it a unique solution for all the CMEs that we look at? Because the flux ropes could have a different way that they get launched from the inner corona and then they show up in the plane of the sky with different morphologies. And is there a problem that we misinterpret some of the, let's say, more intricate things about the structure of the magnetic field if we use one particular flux rope type model?
There is, but well, we have to start somewhere. Oh, Sarah has a raised hand. I wonder if that is a question.
Absolutely, we're always at the limit. We're at the mercy of what model we assume, and part of what we're doing is trying models and then using punch data to learn to the extent that we've got any validity there, and then come up with new models. But I will say that the purpose behind the 50,000 simulations is to address exactly the point you're talking about, because it varies not just the orientation and shape and size and speed of the CME, but also the topology of the magnetic field within the structure. So it is restricted by what the model can do, but this particular approach is providing quite a big variety of possible magnetic structures.
Okay.
Thank you, Sarah.
Okay, so I think we should move on to the next two. Angelos and Joe's talks. So Angelos, there's a big question coming up for you and a discussion between you, Craig, Sarah, but I wanted to get hopefully the easier ones out of the way first.
Okay.
The first one is obviously
Mihir, I apologize. Before we move to Mihir, to Angelos, the super easy question for me about the link to the CME challenge data, and the super easy answer is, guys, email me. It's not a secret. There is no obligation. You will not be imprisoned and put to jail for not for asking for data and not participating in the challenge. If you just want to look at it, just email me. The reason why I'm doing it this way is just I'm interested to get a head count. That's all. So thank you. Mihir, I apologize.
No problem. No problem. So I think this is a comment more than a question. Angelos, did you read it, or do you want me to read it and you can answer it? It's about projection effects, and CME mass and velocity will be higher than the true average. So
yes, yeah, I replied to John. Yes, indeed. That's one of the limitations.
Yeah, I didn't see a reply. That's why.
Yeah, that's indeed one of the limitations of the single viewpoint observations, which I didn't want to go into too much detail. But the saving grace here is that having so many events over so many years, effectively, we have to assume that we've seen all possible CMEs in all possible configurations and directions. Therefore, the range of numbers we're getting must be representative. Now, there are some caveats, particularly for the width. That's why the events have to be cleaned. I didn't take all the events on the list, but I did take, use my own judgment of which events to exclude based on widths. I don't have any halos, any very wide events. And so the masses, the same thing. The masses are always underestimated by a factor of 2 because of the assumptions we make. It doesn't have to do anything with the projection, really. So, I mean, I say the bottom line is that we have seen all CMEs we've seen, and this is the range of numbers that we're going to get.
Okay. There was a question from Christian Mostel about near-Earth sunline and PSP along with other inner heliospheric acids will be sometimes near that line, and there should be some additional imaging in situ when it's quite close to the Earth. So I didn't really understand if there was a question or it was just another comment. I guess it looked like a comment to me.
Yeah, indeed, for doing individual event analysis, that's fine. What I was referring to was the ability to cross-calibrate or validate different methodologies. That's what I was talking about. And for that, you do need a consistent synoptic type of observations like we have from LASCO or from stereo A, so that you can compare many more events. These other missions, as you very well know, are encounter missions. So we get, well, not you're an in situ person, you don't. But for us, it's only we get data every few, weeks, every few months. So it won't be all that helpful. That's my bottom line.
Yeah. Okay. Oh, there's another question for me and you, and I think you can answer that better than I can, which is about, and even perhaps Craig can comment as well, is comment on PUNCH's role and capabilities in imaging HALO CMEs and CIRs that are directed towards Earth. I think we'll have the same limitations as you mentioned, probably. But you and Craig ought to take that question and answer that.
Yes, yeah, true. So for the HALO CMEs, indeed there will be an issue because you're not going to see the bulk of the CME that of the material that comes towards you. You only see the HALO. Of course, that doesn't prevent you from doing some space weather analysis. That's why the polarization. That's where the polarization capability comes in. That's why the C-core, for example, has that capability. Really, is to try to see if the different by looking where the different flanks of the HALO are relative to the plane of the sky to come up with a better estimate of where the CME is directed, along with the UV data. Right. For the CIRs, no, you're not going to get anything that. Directed towards Earth. To get CIRs coming towards Earth, we need to be 40 degrees towards the L4 point.
Yeah. Okay. So I want
to respond to that.
Oh yeah. Go ahead, Craig.
PUNCH will see CIRs as they approach the Earth. Angelos, you've got it exactly right that with polarization, we can measure where the flanks are in 3D, which of course is what's needed. We can't see the part of the leading edge that will actually impact Earth. That's always behind the occulter. And so, there's always gain to be had from an additional out of plane viewpoint. On the other hand, what's really revolutionary is being able to track the thing in 3D without these ambiguities that come from the multiple lines of sight. So there's enough room for everybody to play here. And you know, the out of sun earth line images that various folks are planning to collect will be really important to hammer some of the questions that we find with Punch. But the 3D location is key. As to the CIRs, there's just so, I don't know if you were here yesterday, Angelos, but
yeah, I was.
Okay, good. Yeah. So there's just a lot of unknown there, but we will actually see CIRs as they approach the Earth. So we should be able to get at least some inroads into that vast discovery space.
Well, you see in the CIRs in the far field like you did, Schmidt did, but not this. I thought that question was really addressed towards the space weather implication behind it, and that's what I was mentioning. It's not going to be useful for space weather, but again, Punch is not a space weather mission. You don't have any requirement for that. We just do it the best you can.
Well, I guess there's a question: what's useful for space weather, right?
No. The question was
structure. No, but can we analyze the 3D shape? Yes.
Yeah, the question was much more simpler than space weather. It was just because something is directed toward Earth doesn't mean it's space weather relevant, right? It's about.
I don't care. If it's not direct to Earth, why would we care?
Well, if you want to send astronauts to Mars, you might care.
Oh yes, true point. Good point.
So,
yes.
I mean, so he's just talking about imaging HALO CMEs, which is a limitation of all Earth-based, system observatories. So, the question was what are the roles and comments and capabilities, and maybe we can actually have a list of additional improvements or things that previously we couldn't measure, and put that out in the community that, okay, LASCO did this, Stereo did this, we will do this better. And maybe that's something that we could do, especially in terms of HALO CMEs, which are quite a lot of people interested in. So maybe it's a side topic that we can come back to later.
Yeah, on my last slide, I actually had those points that where Punch will come in specifically for space weather is the ability to have these 24/7 high cadence observations will allow us to develop data assimilative techniques to the heliospheric propagation models. Okay,
so I think we have 15 minutes in this session left, and I have two topics. Okay, there's hands coming up all the time here. Or maybe they're not.
Yes, I just wanted to say there is a comment in chat from Heather who says that we can track the CIRs and know when they will arrive.
Yeah. Okay, thanks for bringing that up. So the main discussion going on in the Slido was about polarization and 3D effects. But I think before I go to that, is Joe Giacalone still on and Bill Matthews still on?
I'm here, yeah.
Okay, so Joe is here, Bill is not. But one question is, let me elevate that, and then we'll come back to this polarization topic, which I think we could spend a lot of time on it. It seems like it from the slide.
Here, just a suggestion. I'll be showing slides on polarization. It'd be a lot easier to have the discussion after that.
Okay, so let's just go through with this and then wrap this up. I think that's thanks for telling me that, because otherwise we could have left the discussion halfway through. Okay, so Joe, I don't know whether you see that. Are these power laws?
Yeah.
Yeah.
Well, which one? Bill's or?
No, you see it up there, right up there. Are these power laws self-similar?
Oh, that's Pradeep's question. Yeah. Okay. I actually just hit a reply to that. So the answer to that is yes and no, as I have in my reply. The yes is that I'm sorry. The power law depends only on the plasma density compression across the shock. That's the only parameter that comes into play here. So to the extent, so it's yes that the plasma density jump's the only thing that matters here. But different shocks have different plasma density jumps, and so that's why you would get differences. But focusing only on strong shocks, there is a sort of a universal limit on the plasma density jump. The strong shock limit is a density jump of 4. So So it's essentially a universal process. So you would expect the power law at low energies at a GCR, excuse me, at a supernova remnant to be the same as at a very fast CME driven shock. So the power law would be the slope, the spectral slope would be the same. So yes, it's universal. It's essentially universal.
Okay. The second was Bill Matthews. He's not here, but we can talk about it.
I'm here, Mihir.
Oh, you're here. Excellent, Bill. Thank you.
Yeah, I also replied to Bill's question. So his question was, do we need to go? So the one thing I didn't say in my talk was that the Parker equation does assume isotropy. So it has averaged over the pitch angle and the phase angle of the particles. And his question essentially, is that important? I mean, should we be going beyond that approximation? And there's SCP models out there that instead of solving the Parker equation, they solve one step back from that, where you don't average over pitch angle and you keep the pitch angle information. And so if you want to understand especially the early phase of these events, the rise of the SCPs as they're coming out, then you have to go beyond the Parker equation. You have to retain the pitch angle information. So that is important for transport away from the shock. The shock acceleration part of it, I think isotropy is a reasonable assumption for the shock acceleration part of it. But the early phase and the transport in the interplanetary space, it is important to the pitch angle information is important, especially if there's weak scattering. Yeah.
How about the second part, Joe?
The drifts, yeah. Well, the drifts. The drifts are included in that as well.
Yeah, well,
maybe you could expand on that, Bill.
Well, there's a lot of acceleration theories that are based on assuming magnetic moment conservation or near conservation and so forth.
Yeah.
But we know that turbulent fluctuations destroy the physics underlying drifts. And it's just a question. I keep seeing papers by a lot of our colleagues that make both of these assumptions.
Yeah.
And I'm just wondering if we might be missing some mechanisms because of constantly falling back on these.
Yeah, you cannot assume conservation of magnetic moment. Okay, so to get particle acceleration, you really do need to be within the accelerating region where there's a plasma compression. Or a strong parallel electric field. I guess there's other kinds of mechanisms out there, but you do need to be in the region where the acceleration is taking place, and you need to be constantly being fed back into that region. And so that's going to happen through particle scattering. I know there's this mechanism proposed by, Don Mitchell's discussed this pressure cooker mechanism where you have mirroring below the CME, and then there's this electric field above it, which I suppose could be one where you might assume conservation of magnetic moment. But it's really, the bottom line is, any sort of turbulent system, you're going to break conservation of magnetic moment. So that's not a good one as an example. But in the Parker equation, I will say drifts are in there. All the drifts are in there. So I know there's a long history to this. So the drift term in that equation does contain the gradient B drift, the curvature drift. Those are in there. It's just averaged over pitch angle. That's all. You just do the integral over pitch angle at the end, and you get that drift term. So they're in there. You don't need to go to, say, the focus transport to get that. But I would say it is important to your point is well taken. You need to recognize the assumptions that you're making. There's other assumptions on the particle motion in restricted field geometries, for example, the particles stuck to field lines and things like that. Yeah.
Yeah, I realize this is probably technical for this audience, but I just thought I'd ask you anyway, just to see what you're thinking about it recently.
No, it's a good question. Yeah.
But people should be aware that assumptions are sometimes broken, right?
Yes, absolutely.
Anyway, thanks, Joe. We can talk about this more at later times.
Yeah. Maybe see you next week.
So Joe, can you hear me? This is Mihir.
Yes. Yes.
Yeah, so regarding the spectral breaks, there was Dick Maywald did this. I did this about, we looked at about 40 odd solar particle events with different species. There seems to be a charge to mass dependence to the spectral break. So in other words, that rollover energies that you talked about, for protons, it would be like, 30 MeV. For helium, it would be less and less and less. And by the time you get to iron, it'd be like sitting around 1 to 5 MeV per nucleon. This is so, there was a charge to mass dependence that seemed to be constrained by turbulence theory in terms of what the power law dependence of that slope would be of the energy itself. So, and Gang Lee did a modeling and came up with some ideas about that. But of course, when it came to the GLE events, the constraint of that power law dependence, which was Q over M raised to the power of 2, was easily broken in 3 of the 6 GLE events that I looked at. So, there is something else going on in these big events that we don't understand. So,
Well, the only point I'll raise here is that yes, the charge matters and in this problem as well. So higher charged particles can reach presumably higher energies, but they're also heavier. So the charge to mass dependence comes in. But all of this depends on the transport properties. So essentially the kappa, the diffusion coefficient.
Right.
So, but that depends on the nature of the magnetic field. Often the theories for kappa assume a certain thing about the turbulent spectrum, whether it's isotropic or whether it's this composite 2D versus slab, or there's all these different assumptions about the nature of the magnetic field. So to make progress on that front, I think we need to know, we basically need to know B, right? The magnetic field.
That's a tough measurement without in situ data at now. Maybe there is ways to do it. The reason is that it is, the charge to mass dependence is an output, as it were, of an equal diffusion coefficient condition between the particles are resonating by some kind of a turbulence. So it is all related. So the question is whether we can constrain it and make further progress.
If I can just add one remark about that thing, the point that Mihir just brought up. It is true that it's nice to have in situ measurements to get measurements of correlation scales, for example. But unless you have multiple spacecraft, you cannot simultaneously get the parallel correlation scale and the perpendicular correlation scale. And that's actually crucial in deciding what kind of turbulence model you want to put in to get the kappas. And if you don't get the kappas right, you're not going to get the transport right. So I actually think that PUNCH might be able to, if we can get down inside a little bit into the inertial range in these crucial regions of the inner heliosphere, we might be able to infer parallel and perpendicular correlation scales if we know the direction of the magnetic field. But you can probably get that from a model, right? But I know spacecraft can simultaneously get lambda C parallel and lambda C perp, the parallel and perpendicular coherence scales.
Right. So I think we ought to close this discussion. It'll be a very good discussion, but I have one more topic that I want to bring up, and that was Angelos raised it, I think, about all senior scientists, and getting the impression that several efforts are reinventing the wheel. How do we make sure that our younger colleagues do not get stuck? I think this might be applicable to across not just the PUNCH mission, but in our field in general. So perhaps we ought to have that, keep this in mind and have another discussion, but not just related, to PUNCH. Maybe we can start that off and say, what's available, what we've done, where are the pitfalls? I don't know. This is a very tough thing to answer. So I don't know, Craig, do you have any ideas on this particular comment that Angelos made? I agree with Angelos that, there is
have a comment on that, which is that, yes, at some level, people are reinventing the wheel. And that's been going on, ever since we reinvented a bunch of wheels coming in as the younger Soho cohort. I see that as a good thing. Science works best when you have overlap between your fields of view. And I think the same thing works in analysis space, if you will. That if there's overlap between you know, the thought processes that older people went through to develop something and that younger folks are as well, that builds a seamless edifice that that generally advances. I think it's important.
Yeah, I think
too. Go ahead. Yeah.
Yeah, go ahead. Finish off, Craig, first.
Okay. Yeah. So I don't see reinventing the wheel, going back and rehashing old techniques with new technology or new eyes is necessarily a bad thing. We just need to be aware of the space, and ideally mentors will point excited younger people to some of the older work so that they're not working in a vacuum. That's all.
Yeah, so I have just a comment on that. I think I'm not worried about people or younger folks. I'm in fact encouraging them as well. Do your own analysis and see if what I did was right. And if it turns out it's wrong, then well, good for you. Go for it. What I'm concerned about is the lack of literature knowledge. Okay, in terms of, I did the same when I was doing the CIR paper back in the 90s with Ulysses. I thought I'd discovered CIRs when in fact they were discovered at Pioneer and Voyager and all that stuff. So, so it's important to have, in fact, the older as well as the senior scientists, as well as the junior scientists, to have a good grasp of the literature, of what's out there in the literature, what's been seen before, what's been observed before. And then, that's just a general statement. It's neither here nor there. But since this is our last point of the topic of this particular session, I thought I'd just bring that up anyway, because it was there.
Can I just say one thing real quick, just to follow on to that, because it's an important point that you're making, but it's also, I have discovered sometimes people, junior scientists sometimes think that something has already been done, when in fact it hasn't been.
It cuts both ways.
It cuts both ways.
It cuts both ways.
Right.
Yeah,
to assume that something obvious now has been done in the past, right? Yeah. Just because it's obvious now doesn't mean it was obvious before. Yeah.
Right.
Yeah. It's cut. So I think, I don't know. I think it's just the way we do our research anyway. So it's fine. Eventually things work out.
So just a comment, you might want to have someone in the younger generation join this conversation. I see Gilly's making some comments in the chat.
Yeah, I see that. I think it's a good conversation to have, but maybe not at this point in time. Maybe towards the end of the meeting in an icebreaker or something.
I want to close with a mea culpa. I was in my 40s when I first encountered Hohenhausen's book from the early 70s on the solar wind. And I think we want to try and avoid that, but it doesn't prevent people from doing new work. And ideally, folks, have mentors that can point them back into the literature. But I think there can be too much of that too. Sorry, go ahead.
Okay, so I think, are we ready for the next session? Or are we taking a break? I can't remember what the agenda was showing.
No, we're going straight into the next, and then there's a break.
All right, okay, let's do that. So I think this is the session 8 with 4 contributed talks, and Annie and I are chairing that session.
Yep.
So the first talk is Hugh Morgan. I think Hugh, are you around?
Yeah, I'm here.
Okay, so we're 1 minute late, but I'm hoping we can catch up at some point.
Okay.
So go for it. So we'll let you, present your 2 or 3 slides for 2 or 3, between 5 minutes or so. We'll have some discussion, and then we'll table much of the discussion till later on. Go ahead.
Okay. So firstly, thanks for the opportunity to talk in this very exciting meeting. I'm not sure if this talk fits with CME and shocks, but we'll see. Using polarized brightness coronagraph observations, we can create tomographic reconstructions. So this is an example in the center here of the type of data we use. It's formatted at a given height, position angle, the azimuth versus time. We need 2 weeks of input data. And over the years, I've been doing static reconstructions. So you have one density distribution on the sphere that best satisfies the input data. And note this is regularized, so it's forced to be spatially, to find a solution that is spatially smooth. If we take this density distribution, we can create synthetic observations. And this is shown in the top left here, and it can be compared to the original observation. So over the past year or so, I've developed a new time-dependent tomography method. This is also required to be spatially smooth and temporally smooth. And we have temporal variations confined to the streamer regions only. So this movie here is showing the streamer belt during November 2018, showing the density variations. Now, if I do synthetic observations from this distribution, I get what's shown here in the top right. And the surprising thing about using this time-dependent, smoothly changing density is suddenly we're replicating the fine-scale fuzziness of the streamer belts in the original observation. So this is an important qualitative point here. Even smooth, slowly changing density variations in the streamer belt can give quite intricate and fine-scale this fuzziness we see in the coronagraph images. So what I've done here is to select 4 points in the streamer belt, and I'm plotting the density as a function of time. And the density variations can be very large. So this red line, for example, is showing an increase here, which is a factor of 3 increase from the mean. And this occurs over 2 or 3 days. So the timescales of these variations are anything from 12 hours to 2 or 3 days, or sometimes 4 days. And tomography is crucial to reveal this variation because, yes, with coronagraph data, we can see small scale rapid stuff, and we can also see slower changes in the coronal structure. But anything on timescales between those 2 extremes, you can never be sure if it's a true density change or due to solar rotation and projection effects. So this is a newish phenomenon. If I plot the density as a function of, the density as a function of time at several heights. So this is for one fixed longitude and latitude over time. And I do this for several heights between 4 and 8 solar radii. What I see is a lag between at increasing height. And the speed corresponding to this lag is around 120 kilometers a second. So I'm thinking of this, I can think of a rigid magnetic structure to the streamer belt, but with density variations propagating outwards. And then this speed corresponds to an outflow velocity. Or I can think of a more or less a constant density relative to the magnetic structure, but the magnetic structure is moving. And then this would correspond more then to a sound speed. And of course, in truth, I don't know which one it is. So, and it could be a combination of both density and structural variations. So looking forward to PUNCH, NIFI is most suited for the current tomography implementation. And I anticipate that NIFI, I can plug NIFI data straight in and get results straight out. But also the Wi-Fi composite field should work. All I need is high quality polarized brightness observations and a regular cadence. At larger distances, I'm most concerned about the F corona. We don't really know what the polarization of the F corona is, but it probably does increase with distance from the sun. The one saving grace is here is that the F corona is much smoother spatially than the K corona, and it also varies less in time. So my take-home message here is, yes, we're all very interested in these rapid small-scale variations on timescales of up to a few hours. And we're also interested in large-scale slow variations over several months or a solar cycle. But time-dependent tomography opens a window to multi-hour, half a day to a few day variations. And this study will be published in ABJ in the next couple of weeks, hopefully. So thank you.
Thank you, Hugh.
Okay. Go ahead, Anna.
I just wanted to say let's bump this the Q&A session to the end of the session, and let's move on to the next speaker. And the next speaker, may I please ask you to pronounce your name yourself so that we know how to say it right?
Yeah, my name is Shatabdu. Shatabdu.
Shatabdu. Thank you.
Yeah. Pleasure.
So the next speaker is Shatabdu, and yes, go on.
Yeah. So, hello everyone. So I'm Shatabdu Majumdar from Indian Institute of Astrophysics, and let us discuss a little about the insights on 3D evolution of coronal mass ejections in the inner corona. So what we do is we select some 59 odd CME events which were observed in the stereo core1 and core2 pair of images. And we implement the well-known graduated cylindrical shell model to this pair of observations to study the 3D evolution of this coronal mass ejections in the lower heights and the upper heights as well. And apart from that, what we also do is we connect every single CMS onto the solar disk, we backpropagate them, and then we connect the CMS to the source regions that they're coming from. And what we do is the identified source regions are then further subclassified into 3 broad categories. The first one are the well-known active regions or the flaring regions. And then we have the prominences. And then we again subclassify the prominences into 2 categories, which are the quiescent prominences from the quiescent region, and then the active prominences. But the active prominences are nothing but we have these prominences with one or both of the foot points connected to active regions. And these are very well-known classifications which have been used earlier in the literature. And one of the main reasons of capturing the active prominence category is that we're still not sure whether to include them in either of the other 2 categories, whether they should be included in the active region category or whether they should be included in the quiescent prominences. And as we follow up in the next 2 slides, you will see more reasons why we say that. So the basic idea about this particular discussion is that we try to understand the 3D evolution of the CMA in the lower heights, and that too we want to do it uniquely in white light because we don't want to get into the ambiguity that whether we track the same features in white light and in UV. Apart from that, what we are also interested is we want to see how the kinematics in the higher heights are connected, or rather, let's say, coupled by the kinematics in the inner corona. In other words, we want to see that how significant it is about observations that we have, because as it goes on, till now, we have very limited observations in the inner corona, and we want to emphasize how important observations of inner corona is for a holistic understanding of the kinematics of coronal mass ejections. So what we do is we study all the 59 events and we fit the GCS model, we connect them to the source regions and we move on. So as we do that, we come here, what we plot is we plot the height time, the speed time and the acceleration time profiles on the left-hand side plot. And we also plot the width evolution profile. And what you see is this is a typical example of an impulsive CME where you see this impulsive phase of the CME with the speeds rising from a very small value to around from 100 kilometers per second to 1,000 kilometers per second within a few seconds of time. And what we observe is, if you see in the 3rd and 4th panel on the left-hand side plot, there is a blue vertical dotted line which marks the height at which the impulsive phase of the acceleration ceases and the height at which the initial rapid expansion of the width also saturates. So what we saw for one particular event is that these 2 heights are lying really near to each other. And to check whether this was just coincidental or whether this happens for other events as well, we repeated this exercise for all the other events. And luckily what we found is we found that the heights at which the impulsive acceleration ceases and the heights at which this rapid width expansion also saturates happens to be overlapping for most of the events. And that is seen in the second plot. If you see here, we have plotted a height distribution of these two particular heights, and the histograms are largely overlapping, first of all. And secondly, we also see that for both these heights, they peak around the height range of 2.5 to 3 solar radii. So as a whole, what we emphasize is, first of all, how important it is to consider the width evolution of the CME as far as an understanding of the kinematics is concerned. And we also see that the width expansion and the impulsive acceleration is nothing but a different manifestation of the same Lorentz force, because it is the same height at which both these phenomena are ceasing and giving rise to a second phenomenon. So and also from this particular plot, we reported that it is indeed the Lorentz force which is responsible for propelling as well as expanding a CME, and that the influence of the Lorentz force for impulsive CMEs tend to lie between 2.5 to 3 solar radii, which is again, strictly speaking, in the inner corona. Apart from that, on the right-hand side, what you see is we have studied the acceleration duration and acceleration magnitudes for all the CMEs. And let me just precisely mention that the quantities that I'm talking about is on this plot are the true quantities, and they are not suffering from projection effects whatsoever. So we see that in 3D, there is an anti-correlation that is valid, which was also reported earlier in 2D quantities, but then we reported that in 3D, it remains the same. And another important point is, if you see that we have color-coded the plot with respect to the source regions the CMEs are coming from. And what we see is the CMEs connected to prominence eruptions, which are in green data points, are mostly located in the lower part of the figure, which tells you that these are the CMEs which tend to be mostly gradual events with very small acceleration magnitudes, but they experience it for a longer duration. Now, as we move on, as we said, that we are also interested in the coupling of kinematics of the CMEs in the outer corona with that in the inner corona. So to have an understanding on that, what we did is we first of all plotted the peak velocity of the CME and the peak acceleration on the left-hand side top panel on the first column, if you see. What we see is in the black fonts, we plot the overall correlation coefficient for all the CMEs. And then in color-coded fonts, we plot the individual correlations for CMEs coming from a certain class of source regions. So the red ones are the CMEs which are coming from the active prominences, and the blues one are the ones from which are coming from the active regions, and the green data points are from the CMEs which are coming from the quiet filaments or the quiet prominences. And interestingly, if you see here, we see that the individual correlation for the CMEs coming from active regions is much, much higher, with a very high correlation of 0.9. Whereas the CMEs from the other two source region categories are much, much lower. And that again tells you a good indication that why it is important to consider the imprint of source regions as far as the statistical understanding of kinematics of CMEs are concerned. And further, that is also supported if you look into the figure in the bottom panel of the left-hand side. We plot the velocity at peak acceleration that is experienced by the CMEs versus the peak acceleration. And once again, the same thing is manifested. As you see that the overall correlation, although gives you a somewhat reasonable correlation of 0.57, yet the individual correlation for CMEs which are connected to active regions are much higher than the other two, with a correlation coefficient of 0.7. So that again gives you an idea that how important it is to consider the source region information for the CME understanding of kinematics of CMEs. Now, moving on the second column, in the middle column, if you see, we have plotted the average acceleration in the outer corona and the mean velocity in the inner corona. Now, this has been well known for quite some time that the average acceleration and the average velocity in the outer corona are anti-correlated. And that's a well-known result because we have this solar wind drag interaction with the CME, and we have known that the faster the CME, the larger the drag it experiences. But then what we found is from our results that for CMEs which are connected to active regions mostly, their correlation coefficient is much higher than the CMEs which are coming from the quiet filaments. And what we see is this, what does this tell us? This tells us that the drag experience of the CMEs which are connected to those active regions, it happens much, much earlier than the CMEs which are connected to the quiescent filaments. So it is the drag experience which comes into play much, much earlier, as early as in the inner corona itself. I think this is something which should be taken into account in the future CME initiation models. Secondly, if we plot the linear velocity of the CME versus the mean velocity in the inner corona, we might agree that this is mostly an intuitive plot. But the importance of this particular plot is that we have found an empirical relationship between the two quantities based on the positive correlation that we have seen here. If you see the middle panel on the bottom hand side. So the take-home message from this particular plot is that if we can extrapolate the linear speed from the mean speed in the inner corona, then we would be able to feed in this linear speed into the CME arrival time models. And why do we want to do that? The reason that we want to do that because there are space missions, for example, the Aditya L1 mission of Indian Space Research Organization, which will not be having any observations of the outer corona as such. So for missions like this, will it be possible to use the observations of inner corona solely and independently for arrival time predictions of CMEs? Well, primarily as it stands of now, we say that we can do a back of the head calculation. And the important part of this particular figure is that we can extrapolate the linear velocity without using the observations of outer corona. And that will help us in minimizing the lead time of forecast. And that is something which is really important as far as our preparedness is concerned. But again, let me just say that the accuracy of this particular model that we have given here that has still not been tested, and we are waiting for some real-time data, and we're looking forward to that as well. Also, I would like to emphasize is that if you see these two particular distributions on the right-hand side, on the third column, we have plotted the mean speed distribution in the inner corona and the outer corona. And what we see is the speed distribution changes, or rather it shifts towards the right-hand side.
1 minute for me.
Thanks. So the speed distribution shifts towards the right-hand side, towards the higher speeds. So that this again tells you that will it be really wise to tag a CME with a single average speed, because indeed the distribution itself changes as the CME propagates from the inner to the outer corona. And lastly, what we also found is once we plot the distribution of the height at which the CME reaches its peak accelerations and the peak velocities, what we see is the green distribution, which is the distribution for the height at A max. We see that the distribution again peaks between 2 to 3 solar radii, and that again tells you that it is indeed the Lorentz force that is mostly responsible for propelling the CMEs to reach their peak accelerations, apart from their impulsive acceleration phase. So the take-home message is that the imprint of source regions is really evident, and I think these things should be taken into account, and that the kinematics in the outer corona is largely coupled and connected with that in the inner corona. Thank you so much. That's all I wanted to say.
Thank you for the talk. And again, let's defer the Q&A until later in the session. And let's move on to the next speaker. The next speaker, may I please ask you to pronounce your name so that we know how to say it right?
Hi, I'm Ritesh.
Ritesh, thank you. And you have the scene.
Okay, my screen is visible, right?
Mm-hmm.
Yeah, okay. Thank you everyone for giving me this opportunity. So my topic is automated detection of accelerating solar eruptions using parabolic Hopf transform. So I have few collaborators which I have listed here, and a list of institutes where they are associated with. So my talk is mostly associated with detecting especially the accelerating eruptions. So here, by eruptions, I am not distinguishing between whether they are UV counterparts of CMEs or CMEs themselves. Initial target was to identify this accelerating CMEs. Therefore, the name which we had given for this algorithm was CMEs identification in inner solar corona, or in short, CISCO. But as we know that we have limited observation of CMEs, so we started with some UV counterparts. So here I will first briefly describe how this algorithm works. So we took the wide field of view image of SWAP for demonstration, as you can see around here. And then we did radial filtering and master disk, as we were mostly interested in off-limb eruption eruptive events only for the time being, because as we know that the field of view is limited and it is in emission wavelengths. So we chose to go with the off-disk eruptions. So after radial filtering, you can see that the features are widely seen within this particular field of view. Then we converted these images to polar coordinates. And here you can see the height in y direction and spread over the different position angles. Here in the inner corona, we are also facing, we know that there are different features such as coronal loops, which actually like kind of overshadows what actually for the eruptions. Like you can see here in the right hand side, there's an eruption, but there are other structures which are equally bright. So we employed the Fourier motion filtering, which has been widely used and mentioned in DeForest et al. 2014 and subsequent papers related to HI images. So you can see that we have suppressed significantly the contribution of the loops, and only the erupting structure that is moving upwards in this height time height r theta diagram has been brought out. Then we summed up all the intensity in the previous images along this vertical direction, so that along the position angle we get the summed up intensity like in this particular plot. So here you can see that at the location where the eruption was present, you can see that a sudden rise in the peak, whereas in the other locations it was mostly limited to the background level. And once we have this 1D intensity image for a single time, we stacked such images over the time. So you can see that in the X direction, it is the position angle, whereas in the Y, it is the time. So we can see that because of the motion filtering, there are certain regions that may or may not be the location of the eruptions. And there is one bright region which where we already saw in the summed up intensity plot, there was a bump, and that may have been the reason for region where the eruption may have been present. Then we did intensity thresholding and also labeled these regions. We put a criteria here that if the eruption is wide enough, greater than 5 degrees in width, and also persistent in time for at least 3 frames, then only we will consider that region for further identifying and characterizing those eruptions. Then we generated the height time plot. For this particular example, the height time plot looks something like this. And from the preliminary observation, you can see that it is somewhat like kind of a parabolic in nature, which is actually the nature of any accelerating object with time. So then we applied the widely used Hopf transform, but now in the second order. So already existing algorithms like Cactus is based on linear Hopf transform and has been widely used to characterize the CMEs, especially in the outer corona, like in LASCO C2 and stereo core 2 observations. But here, since we had been observing in the lower corona close to the sun, and it has been widely known that eruptions mostly accelerate. So we try to extend the application of Hopf transform, introducing a second order identification, which is parabolic in nature. And then later we recorded their kinematics and other properties. So how did this transform work? So as for this particular example, we try to identify the parabola of this form, where R is the height and T is in the horizontal direction. Here we have some free parameters, which we need to actually find out through this computer vision algorithm of Hopf transform, which are R0, T0, S, and the theta. So based on the paper of Ballard 1980, which is for generalizing the Hopf transform, we get this set of parameters for a parabola. So here we did made some assumption because we had to compute this Hopf transform in 4D space. So we assume that means we fixed that since we had master disk up to 1 solar radii, so the R0 we set to 1 solar radii, and the theta parameter which we took for 90 degrees for detecting only the accelerating kind of parabola. And then we use this equation, which is generally kind of reduced from 4D space problem to a 2D space problem, and we try to identify this kind of parabola. So once this is done, and we ran it, and you can see that our algorithm tried to fit this ridge, which is observed in height time plot, as overlaid in this red color line here. So it kind of agreed very much with what has been actually observed. So this is kind of an automated algorithm that can actually capture any accelerating feature. So we calculated the average velocity and acceleration from this particular algorithm, and then we extended this to different data sets with field of view of AIA in different pass bands, and also in UV with extended field of view UVI and SWAP. So there are certain false detections. So currently it stands to around 67% accuracy with some 30% or 33% of false detections. And this results has been published in this particular paper. So one can refer to this for further details. And also, since this work has been only limited to the inner corona, so it can find applications to Aditya's VLC coronagraph, which is observing the inner corona, and also aspects on board Proba 3 for automatically identifying the solar eruptions, including the CMEs, and characterizing them. The next step, which we had been looking forward, is to generalize this so as to extend from the inner corona to the middle and even into the heliosphere. So for that, we are working on a generalized Hopf transform so that we can capture the complete profile of these kind of eruptions that are originating from the lower corona and that can be tracked further out into the heliosphere. So that will be the next step which we are looking forward. So that will be like kind of an extension of Cisco. So that's it from my side. Thank you.
Thank you very much. The Q&A will be after all the talks. And now the next speaker is, may I ask you to pronounce your name, please, so that we know how to say it?
I guess it's me, Bin Zhuang.
Bin Zhuang?
Yeah, and then let me share my screen. Could you see the slide?
Mm-hmm.
Okay, cool. So, hi everyone, I'm Bin from UNH and supervised by Neurox, and I would like to thank everyone and thank the community for this opportunity. And this presentation is just started from a tiny project which is focusing on the moderately fast CME, which can experience continuous acceleration in high corona. Previously, when you go to search the CEDA website or CEDA catalog, you can find some events, some fast CME events with speed around a few hundred km per second. Those CMEs will experience the continuous acceleration, though the magnitude is not very large, but they will be accelerated in the whole LASCO C2 and the C3 like OV. And then we collect those events and found one specific event, which is on 2013, February 27. This eruption may help us to understand a specific topic, which is the role of the magnetic reconnection in the long duration acceleration and the expansion of coronal mass ejections in the high corona. Previously, we know that the role of magnetic reconnection in CM acceleration has been widely discussed and studied, especially for the acceleration. And when many studies talk about the acceleration, they're just measuring the leading edge of the CMEs. And we know that CMEs have strong expansion in the corona, and the expansion speed is sometimes is comparable to the propagation speed. So if you're measuring the CME leading edge, you must consider the bulk speed or the CME propagation and the expansion simultaneously. And thus, you say that the role of magnetic reconnection in this CME acceleration is just a combination of the acceleration itself and the expansion. And as for the role of the magnetic reconnection in acceleration, we know that it will reduce somehow provides the additional Polaroid flux and reduce the pressure of the overlying arcade. And as for the expansion, I show a image here. It is that it provides additional Polaroid flux to the outer shell of the initial flux rope, and thus it will somehow increase the size of the additional size of the flux rope. And of course, the expansion is always due to the balance between the its inner force and outer force. And then when you calculate the leading edge of the flux rope, then you will consider the acceleration and expansion simultaneously. And as for this event, it is an ideal limb event observed by LASCO C2 and C3. And then because its propagation duration is nearly to the 90 west, and then we just measure the CME locations of its core and its front locations in LASCO FOV. That's with the minimal projection effect. And then we see the CME has a beautiful structure with the buried front and a vent shock and a buried core. And during the calculation, during the measurement, we assume that we make an assumption that the buried core is roughly lies in the axis of the CME, and we will discuss this assumption later. And the right figure, the top three, shows the measurement, which is the height time and speed time and the speed height measurement. And you can see from these two panels, which shows the CME has two acceleration phases. One is the initial impulsive one, and the late phase is a gradual acceleration phase. And we focus on the late phase, the gradual accelerations, semi acceleration phase. And the fit shows that, like a linear fit to the speed time profile, shows that in the late phase, the CME also has continuous acceleration, which extend, for example, the front, which extend from for a few hours, 4 or 5 hours, and from like 6 or 5 solar radii to 25 solar radii, even though the CME speed is large, like around 600 to 700 km per second, and faster than the solar wind speed. So the result shows that, in general, shows that the CME, this is a moderately fast CME with speed larger than the solar wind speed, and it has continuous acceleration in high corona from like around 10 to 25 solar radii. And then we go back to the eruptions observations on the solar surface by stereo A. This is the location of stereo A. By stereo A, and we can see we can find the signatures of magnetic reconnection occur on the solar surface, like the cusp and the bright ribbons, and we plot like the flat curve of the UVI observations and the slit of the two bright ribbons, and the long duration separation of the ribbon of the ribbons and the light curves, which indicates that the magnetic reconnection may also last for quite a longer time. And then this long duration of this long-lasting magnetic reconnection will contribute like to the dynamic evolution of the CME, especially, for example, to the expansion and to the acceleration. And then we go back to this panel again. We can see that the CME front is experiencing continuous acceleration, but the core is at a constant speed. At a constant speed. So it may indicate that what you observed in the accelerated CME front is just caused by an additional CME expansion, because, for example, if there is an acceleration like for the front and for the core, then due to the magnetic frozen condition, the core should experience acceleration at the same time. But the figure shows that it's just the front has the acceleration, but the core keeps at a constant speed. So when we like calculate the acceleration speed of the front and the acceleration speed of the core, we can get the acceleration speed for this CME additional expansion. And then we know that there's reconnection, we know there's additional expansion. Then how about the acceleration itself? Then we use solar wind drag force model to estimate the acceleration. Let me explain it. Because the CME, we know that the CME is faster than the solar wind speed, and due to the solar wind drag force, the CME will be decelerated. And then as we see that in the like the speed time or speed height profile, the CME doesn't experience deceleration. So we assume that the deceleration caused by the solar wind drag force is all compensated by the magnetic reconnection contribution to the acceleration itself purely. And in the solar wind drag force model, it requires the solar wind parameters and the CME parameters. As for the solar wind
1 minute warning.
Yeah, sure, I will. And as for solar wind parameters, they are derived by MHD simulations, and for CME, they are derived from observations. And this is a ratio for the deceleration speed of the solar wind drag force model to the additional expansion acceleration speed just shows the comparison, the contribution of the magnetic reconnection to the expansion and to the acceleration separately. And the result are shown here, which is a moderately fast CME experience long duration acceleration in the high corona, and the contribution of the magnetic connection to CME expansion is comparable to or even larger than that to the CME acceleration. And there's some points to be discussed later, which is about the structure of the CME particle, the connection contribution to the expansion and acceleration in low kernel, and how the magnetic connection will contribute to CME when the CME is at very large distances. How about the reconnection size, reconnection rate, and the force acting on the CMEs. Okay, thanks. That's all.
Thank you very much. And we still have a few minutes until the end of the session. Well, we actually have 13 minutes until the end of the session. And I propose to go to the question and answers posted on Slido. So let's go in the order of the received. So the question from Sarah to Hugh, can you comment on how time-dependent tomography helps with the issue of the F corona? And Hugh replied in Slido. And Hugh, would you like to summarize it yourself?
Yes, since we have the maps of the density structure at several distances from the sun, we can look at the density we estimate for the large, fairly uniform low density regions, the coronal holes, at several heights, and then using a mass flux constraint and assuming the solar wind is either constant speed or accelerating, we can see if there's too much mass within these, that the mass increases too much in these low density regions. So we've done this for one case, the November 2018 case, and we do see an excess density. You know, we can never be sure if that's due to the F corona or due to some calibration error, but I anticipate the increasing polarization of the F corona must contribute to that excess density. So then we can actually estimate that polarization. So we've made an estimate of around 7%, but it has fairly large error bars.
Oh, thank you very much. And the next question is for the next speaker, actually, for Shadabdu from Sarah Gibson. How do you see PUNCH data helping you in your study of coupling of the inner and outer corona CMEs? And there is no reply. Would you like to reply?
Yeah, thanks. I was just typing my reply. Anyway, I'll just sum up my reply here as well. So, I mean, it's a nice question again. So what we can do is, first of all, the observation from PUNCH will help us, first of all, to check the credibility and hence the accuracy of the empirical relations that we have proposed here. And secondly, another most important point is we can use PUNCH observations to come up with new empirical models and empirical constants where we can connect the properties of CME kinematics in the inner corona with those of the outer corona and further with the heliosphere. And that is something which has been missing in the field because we don't have a close connection. We have works in the inner corona and we have it for the heliosphere, but we don't have a good connection in the middle. So I believe that's where the PUNCH observations will come in, and we can use our profiles or the empirical relations that we come across to check the credibility.
Oh, thank you. And the next question for you is from Anvesha. I apologize for mispronouncing possibly, but the question is, do you derive the height time profiles for your CMEs from projected white light images, or do you have any other methodology? And
right.
Do you have a...
Yeah. So the height time profiles are derived from the measurements using the GCS model. So that is basically gives you the true height. But again, let me just mention that we have used 2 vantage point observations. And if you are aware of the GCS model, then 2 vantage point observations does not enable you to constrain all the model parameters very well. But then again, since we are mostly interested in the radial propagation of the CME rather than the lateral propagation as such, so we believe that 2 vantage point observations is enough to estimate the height of the CME and the height. So to answer your question directly, the height we are talking about is the true height and not the projected height.
Thank you very much. So there are 3 questions for Ritesh and just 1 question for Ben. I propose to first go to Ben because it's just 1 question. It's from Sarah. How do you think you could use PUNCH observations to relate large distance CME dynamics to their connection at the source?
Yeah, yes, I think this is a good question, but yeah, previously we were interested in the CME dynamics in the high corona is that we found few events which shows the the continuous acceleration of the moderately fast CME is from just in from last C2 and not to last C3 FOB, and we would like to say that if we could use PUNCH observation to extend the same dynamics in a much larger distances, for example, to see how the acceleration will continue and how when the acceleration will stop, that would be very interesting. And now with the combination of stereo and stereo and the set 1 point observations, which may be better to link the whole evolution of the whole dynamic same evolutions together, and from yeah, especially in the high corona or to the even in the independent space. And previously we used stereo high, and we want to search for example use stereo observations to see that when the acceleration will stop, and only very few events we could find, and this will challenge the whole whole topic because we don't know we don't have large amount of samples. So if we could collect more and more data and events, then that will help us to understand the general same dynamics, from the even from few solar radii to even 40 or 50 solar radii.
Thank you very much. And there are 3 questions for Ritesh. And the first question from James Toppin, the second order, how sound like it will be useful for the outer heliosphere, where projection effects make the high time plots curve. And there is some discussion in Slido. Would you like to summarize your answers / discussion?
Yeah, so we are looking forward to apply this Hopf transform to a degree further. So currently, since we are only focused on the lower corona, but as he mentioned that in the outer corona also the high time profile gets curved. So there the challenge is from the say plus S, so the shape changes in the kind of inverted J. So that will be a kind of next step if we can combine identification process that can identify both the lower corona as well as in the outer heliosphere through a single automated algorithm. So yes, we are looking forward to it. So we are on it.
Yeah. Thank you. Another question from Craig about the parabolic Hall transform that you applied to your JMaps is intriguing to Craig. And what extensions do you anticipate for the wider field? And would you like to summarize your replies?
Yeah, so I think that is kind of a link to the previous question. So yes, so the next step, first we are focusing on especially on the K-core data, which is again the white light CME observation. But yes, as I mentioned that for the wider field, using the stereo heliospheric images, we are currently working that to capture those kind of inverted J kind of features, so that we can capture these kind of CME profiles. So for this, we are trying to extend this second order Hopf transform to a generalized version. So the challenge there comes since we are trying to capture the different variations in the CME kinematic profile. So the number of free parameters is also increasing, but we are onto it so that even in the heliospheric images of a stereo and in the future with the PUNCH and even the L5 heliospheric image, we will be able to capture those kind of kinematic profile of the CMEs.
Thank you very much. One more question from Hugh about which language did you use, whether you wrote your own second order, or is there some library? Would you like to summarize the answers?
Yeah, for this, I developed this code in Ideal myself. So earlier work included identifying the piecewise linear Hopf transform for the second order images, but then I used ideal, so inspired with the linear Hopf transform, though it is written in C, but then I went one step forward with ideal.
Thank you very much, and thank you to all speakers. And we still have a few minutes. If people have any more comments or questions, feel free to either raise your hand and speak here, or also enter questions in Slido. And there is a raised hand from Dave Webb.
Hi. Yeah, related to Angelus's talk and also Hugh Morgan's. I'm very interested in the, I think, topic that nobody's really discussed in detail yet is the relationship of CMEs in general in a global sense to streamers and to the streamer belt. Angelus and I have studied streamer blowout events, which become streamer blowout CMEs. And so the question is, you know, I've always wondered how are these streamer blowout CMEs related to the evolution of the streamer and the streamer belt in general. And Hugh's presentation is pertinent to that. Of course, he wanted to avoid short-term things like CMEs in his model. He's looking at synoptic data, but it'd be nice to relate CMEs to that. And this also relates to the fact that CMEs, that streamers, the streamer belt kind of forms the base of the heliospheric current sheet. So streamers, some streamer blowout CMEs, when they're ejected into the heliosphere, are actually bubbles injected into the heliospheric current sheet. And I think PUNCH and affiliated data should be able to give us a lot more information on this whole global aspect of CMEs and the heliospheric current sheet, and also in a sense to CIRs, because as far as the slow wind is concerned on one side of the CMR, the CIR compression region, those are often coming from the streamer belt. And of course, CMEs will come out through those areas also. So just a comment, I think, on something that the PUNCH could be, PUNCH observations to really help us with.
Here?
Yeah, can I quickly share my screen just to show an extreme example of what David is talking about? So this is showing at a given height, azimuthal position angle and 2 weeks of time along the y-axis. And if we look at here, we've got the streamer belt and then a large CME. And then we can see the streamer belt has jumped by, what, 10, 20 degrees and stays there. So that's exactly one of the problems with tomography and the time-dependent tomography, are these large CMEs that actually disrupt the streamer belt. And I was always under the impression that the streamer belt would gradually return back to its original configuration after a CME, but obviously that's not the case. In these extreme cases, we see a shift in the streamer belt position and it stays. It's a catastrophic change in the streamer belt configuration.
Craig?
Oh, just to build on what Hugh just said, Hugh, we shouldn't really be, in retrospect, we shouldn't be too surprised about that, right? Because the CMEs are actually reconfiguring the boundary condition. But that's a really great demonstration.
Thank you, Craig. We are running towards the end of this session, and I think we now have a 10-minute break, right? And
that's right, 10 minutes, right on schedule.
Oh, Angelos has a raised hand, actually.
Angela, you're keeping us from our break. Can you wait till the next one?
Yeah, well, no, it was up to continuing on David's question, because it is there's an important aspect of those streamer blowouts, which I think that's what David was driving at. There is a continuity of ejection starting from the streamer blowouts, for the streamer blobs to the streamer blowouts, okay? that have to do with the configuration of the global magnetic field. And these are distinct from the CMEs that occur in active regions. Okay, so they are different, in a sense, different physical mechanisms at play. But other than that, the steam blowouts is just a way for the sun to remove excess helicity, more than say excess magnetic energy, which is what is happening in the active regions. So from that point of view, steam blowouts in a sense are a macro CME, a different scale CME. And depending how much you extend that time scale, you will find ejections that, which I think I've discussed in the past, that they occur over 3 days to a week. Okay, so you start from a CME that can happen over a few seconds, right, in an active region, and you can get down to weekly scales that are more related to the global reconfiguration.
Thank you, Angelos. Let's actually go for a break right now. But the Slido keeps live, and there is some more discussion going on there. And let's reconvene in 10 minutes.